How to redo this real quick because just noticed that this problem refers to problem number 19, which hopefully you still have in your notebook. All right, so we're going to answer this question is how is the equilibrium constant for the forward reaction? How does that compare or relate to the equilibrium constant in the reverse direction? So did they switched it up on us? All right, I kind of wish they didn't do this, but if we use this original equation, uh, I wanted you to see that the reverse reaction is that way. And what they did was they just rewrote that for us in the forward direction. So it's a little bit confusing because they're asking us to compare forward and reverse, but they've flipped it around for us. So hope that made sense. All right, so the Kc for the forward reaction is what we just did in the previous problem. All right, I'm going to, you know what I'm going to do? I'm going to erase this. I'm going to erase that and just copy this thing. All right, so now it's less confusing, right? To me at least. All right, so the forward reaction we just solved in problem number 19, and that's going this way. Now the reverse reaction is going to be the opposite way, like that. So this is now the products, and these are the reactants. If you look at in the reverse direction. All right, so we're gonna calculate the Kc, the equilibrium constant. Now the products, we're still going to write on the top the concentrations of the products is going to be the nitrogen concentration times the hydrogen concentration. That's going to be raised to the third power because of the coefficient in the balanced equation, and that's going to go over the concentration of the reactant, which is ammonia, and we're going to raise that to the second power because of the coefficient in the balanced equation. So the numbers given were the same numbers earlier, so let's just flip this around. Right, so 0.25 and 0.15. 0.25 moles per liter for the ammonia, for the nitrogen, and 0.15 to the third for the hydrogen, and what was the ammonia? 0.1. Forgot my units, but they're not going to matter because equilibrium constants don't have units. For a reason we'll maybe explain in a later video. Okay, so let's punch these numbers in our calculator. Actually, it's just going to be the inverse of our previous answer. Anyway, let's just punch these in. We're already almost done. Okay, 0.25. Oh, let me get a parentheses in there. Start over. Parentheses, 0.25 times 0.15 to the third, close parentheses, and divided by 0.1 squared. All right, so I get 0.08, I'm going to round this to 2 sig figs, 0.084, or if you want to write that in scientific notation, it's 8.4 times 10 to the -2, and that's going to be your equilibrium constant in the reverse direction. Now, how are they related? Like I said earlier, they're just inverses of each other. In other words, if you put in your calculator 1, let me do this, 1 divided by the answer we just got, it'll give us the answer to problem number 19, which was 11.85. Or if you take 1 over, let me do it right here, 1 over 11.85, and all those decimals, we rounded that to get to 12. All right, then 1 divided by 11.85, then you should get this number, which you do. So they're related because they're inverses of each other. Now, what is this? What does this mean? Let's talk about that. Well, it doesn't tell us the conditions as far as temperature and pressure, but the equilibrium constant expression, it tells us the constant. It tells us the relationship between the concentrations of the reactants. I'm sorry, the products over the concentrations of the reactants. All right. So if this number, if Kc is big, all right, we'll say it's greater than 1, much greater than 1. If Kc is much greater than 1, and we're talking like 10 to the third, like more than 1,000, then it's going to heavily favor the products, right? Products favored. Products favored. And if the Kc is much less than 1, like 10 to the negative 3, then the reactants, that's what that means. Reactants are favored. And hopefully you can see that, because how would we get a very, very, very small, what am I saying? I'm not favored. All right, what was I saying? So what scenario would Kc be very, very small? It's because the reactants concentration was very, very big. So that's the concentration of the reactants, or concentration is favored. Okay, and if it's somewhere between, then you'll have a good amount of both. All right, it's hard to say because we're a lot of times squaring and cubing these things, so that's why we're given a lot of room for flexibility here. So I hope that conceptually helped.